So, okay. I'm still trying to get things set for your very last regular project. I guess it'll end up spilling into next week as far as doing it. But I think it's probably a good thing for us to do, and I'm going to kind of talk about the sorts of things we're asking you to do in there. In some ways, it's not extremely taxing. You just have to take a little time to go through things, and we'll see that today, an example of that. Okay, so one of the things we want to talk about with this multiple regression is this idea of trying to use it wisely, because again, we have lots of columns of data. So the idea is we have a bunch of these columns of data. These are all sort of explanatory variables. You have a response variable, and you have all this data like this, and we can throw it into this linear estimation command, this line S, and we can just do it. I mean, it's just not a big deal. We do it just like we did with the two columns. It's just when we insert the explanatory variable, we just highlight all these columns. That's the only difference. We have to make room for it, but we'll see that. And so last week, we talked about the adjusted R squared. So when we do the line S command, we get this thing R squared. And remember that the R squared is, so our R squared is giving the proportion of the Y variance, okay, the response variable's variance, explained by the linear model. Okay, so that's, that R squared, it's a good thing to know. But we talked about the adjusted R squared, and what we said was we used adjusted R squared to help with column selection. Okay, and that's what your text does. It talks about this overfitting and underfitting of data, and that we want to look at the adjusted R squared to help us there, not just the R squared, because pretty much if I keep throwing columns of data at the problem, if I just collect more data on more things, actually I'll probably get the R squared to go up all the time. But the adjusted R squared kind of penalizes you for using more columns. And so, just because I used a new column of data doesn't mean it was that helpful. And so we can look at the adjusted R squared there. And that's what your textbook goes into that quite a bit. Now what your textbook doesn't really go into, unless I'm forgetting something about the text, but it doesn't really go into another aspect of looking at your columns of data, and that is the covariance between your explanatory variables. Okay, so we want to talk about that a little bit today and kind of see that. I've got a nice data set on birth weights that really looks at or forces one, should force you anyway, to look at this covariance idea. And so we also want to talk about covariance of explanatory variables. And the thing we're looking for here is, if you think back to the last module, right, we looked at a surrogate. You know, one variable was sort of as good as another, right? We looked at the IMR, the infant mortality rate, and we asked, hey, is that a good enough measure to replace the DALE, which I don't remember exactly what all that stands for. But could we replace the one variable with the other? Well, in a way, that's kind of what the covariance is looking at, is it's taking every pair of our explanatory variables and it's asking, you know, is there so much dependence between a couple of these explanatory variables that maybe we should just throw that column out? Because if one is just a multiple of the other, so let's look real quick at the mathematics of it. You know, suppose I've got two columns and I call them x1 and x2, and I'm trying to come up with this b1x1 plus b2x2 plus my intercept a. So if that's the model I'm coming up with, but it turns out that actually, you know, I can write x2 as 2x1. Okay, they're closely related that way. I mean, it might not be exact, but say I did a least squares on it, a linear estimation on it, and it came out that, oh, a really good model for that would be x2 is just 2x1. Well, notice then that in essence, well, I'll put it over here now, I guess. In essence, then that model I was trying to do is really this, b1x1 plus b2 times 2x1 plus a. But now I do a little bit of algebra, and I have b1 plus 2b2 x1 plus a. Right? I might as well just look for one slope. Okay, because if these things are related like that, why put them both in? And actually, worse than that, when you start doing the mathematics that's involved and you have this kind of dependency, you can actually start getting some really bad answers. Because the mathematics just doesn't like it that you're using all these repetitive sorts of things, these dependent variables. And so we want to look at that. Now, typically, if you're using software, what they do is you can throw a bunch of columns of data at software and say, I want the covariance matrix. And so it gives you something called this thing, a covariance matrix. It's a big table. And normally it's got either ones down the diagonal, or it might put names in there or something like that. So here's column 1. Here's column 2. So it could put names in here, because what we know is the diagonal of this thing should always be a 1. They should be ones, because what you're asking, and we'll see a picture here in a minute, but what you're asking is, is column 1 dependent on column 1? Well, something's really wrong if it's not, right? I mean, they're perfect. If I know X, if I know the first number here in column 1, I know the first number here in column 1. I mean, they perfectly predict each other because they are one and the same. Now, so you would get numbers on that would look a lot like correlation coefficient, so R, not R squared, but R. But we can do it graphically as well. So I could set something up like this, where, here I say there's column 1, here's column 2. These are just labels. Column 3, and say I've got 4 columns, column 4. Then what that does is it breaks this thing up into all these squares for the grid, and I only have to do half of this because the way I can do this is I could make a little graph here, and this would be C2 that way and C1 that way, and then this would be C1 that way and C3 that way, and C1 this way and C4 that way. So I just make a graph with all these different combinations. And what I'm looking for is something like this. Suppose I see a really nice association like that. Now, what you'd rather see, is just that big block of data with no dependency whatsoever, right? So this is good, this is bad. Well, at least bad in the sense of my model. And so, anything that looks dependent, I probably don't want both of those columns in my data, and I could choose which one I want to keep. And I'm hoping to see things that look very independent. Okay, and this is this idea of a covariance matrix. What we could do is we could make these graphs, whereas typically what software will do is spit out a number, the correlation coefficient that goes with that graph, okay, or those data. And again, so bad is if we see something highly dependent. Good is if we see independence. Okay, and that's the type of thing we're looking for. So that's the covariance stuff. Now, so in practice, what does that look like, and what might we do? Okay, so I will switch to this data set. So here I have a data set. It actually comes from the authors of your textbook. These have the father's age. So this is all about birth weights in babies. So we have in column A the father's age, column B the mother's age, C the weeks pregnant at delivery, D whether the baby then was premature or full term, the number of prenatal visits, the weight gained by the mother, the weight of the baby in column G, the sex of the baby or gender, just female or male in this case, which typically at birth, I don't know that we have any other answers, no matter what your feeling is about later in life. But and then smoking, whether the mother was a smoker or a non-smoker. So these are just some data. But what a person could ask, for instance, suppose you were asking the research question, does there seem to be a relationship or an association between whether a mother smokes or not and the weight of her baby? Okay, because generally you don't want light babies, you want heavier babies, and so one could ask, well, does smoking seem to go with an increase or a decrease in birth weight? And so that might be the question. Now, these data sort of aren't really set up that way. I'm going to go to the next sheet on here in a moment. But I'm going to start with, this is slightly different than Tuesday's lecture in that Tuesday I kind of, after I'd done some things, I made the realization that a lot of data are not filled in for the father's age. And so if you get rid of those data to begin with, you lose a bunch of data. Those lines, those observations. But so here, what I want to show you is first, if you do some of this correlation idea, I really meant to say covariance idea. Think about father's age and mother's age. Okay, if you heard the mother was 27, you probably wouldn't expect the father to be 62. Right? You might not even expect that father to be 42. You might expect that father to be somewhere between like 23 and 31 or something like that. If you heard the mother's age was 27. If you heard the mother's age was 40, you might expect that then that the father might be like 35 to 45 or something like that. Now, might not be, but that's probably what you would expect from experience knowing people having babies. And so we can do that, and what I did, I simply highlighted both columns, and I said insert a chart. Now I'm not going to do that at this point because I already made the chart. But notice if you, so the y variable here, the response variable is the mother's age. The explanatory or predictor is the father's age. And now I didn't actually run a regression on that to get a p-value and an r-squared and so forth. But I'm reasonably certain it would be very significant. Okay? I actually did that for a couple other things, so we can see those. But in this case, we don't need the father's age in there. If we know the mother's age, we pretty much know the father's age, is what this is saying. Okay? So everybody get that? That, we're looking for this. And really, to be complete, I ought to get a p-value and look at the r-squared and so forth. Because it's really both, in that if I'm really sure this p-value would be small, it would be significant, and so that might be enough. But if the data were even more spread out than they are, at some point, I might say, well, yeah, there is a dependency, but the variance is so high that maybe I ought to keep both variables in there. Okay, so you could say that. But here, I decided, okay, I'm going to just throw out the father's age and get rid of that column. Okay, so that was the first thing I did. And then I also had to do a little bit of other cleaning. But so there were a couple of other rows that had some missing data in them, so I had to get rid of those rows, but not too many. So this is 147 observations, and when I run it this way, I go ahead and do that linear estimation. Now, the big thing you have to remember is notice the order of the columns here. And every time I put something like this up there, I try to remind you all and myself. Notice this is mother's age, weeks, premature, and all that. In that order, smoking is last, and then weight is the response variable, so I put it as last. Now, here, when I labeled these, they are in reverse order. Okay, so the first slope that comes up on the left was the rightmost column of data. Now, not your response variable, but of the explanatory variables, and so forth, and it goes over, and then the last thing is always the intercept. Okay, so I ran that, getting rid of the father's age, and what I'm interested in, again, is the question of does smoking seem to have some association with the birth weight? And now, and I glossed over something else here. So, again, notice the raw data. Now, part of the reason I like this is you all have a final project. One of the items in the final project says, hey, show us what your data would probably look like. Well, it would probably look something like this, right? If you do a survey or something along those lines, right? Generally speaking, say you are taking data, and in particular, maybe you're doing a survey, so you're having your respondents fill out the survey. If you ask a person, you know, what's the gender of your baby, and you tell them, oh, put a 0 for female and a 1 for male, that's going to be a disaster. Okay? If you have somebody fill out a survey, give them something they can read and do, and don't make them think, right? You know? And so you would get data like female, male, that kind of thing, or smoker, non-smoker, that kind of thing. So this is another aspect of this. Here my explanatory variable that I'm most interested in, the smoking, is a categorical variable. Okay, categorical explanatory variable, numerical, because it's the baby weight, is the response variable. Typically, we just say, oh, that's an analysis of variance. That was chapter 5, right? Chapter 4. I don't remember. What is that? Chapter 4, yes. Module 5. So that'd be an analysis of variance, except I've got all these other possible confounding variables. I mean, certainly an obvious confounding variable is how long was the pregnancy, right? A pregnancy that's full term, 40 weeks, that is going to have a bigger baby than a pregnancy that's 20 weeks. I am really sure of that. Okay? That's a confounding variable. You have to have that in there. Okay? Oh, but that's numerical, and so now we've got this big mix. Well, that's the great thing about regression. I can use the dummy variables. Now, the only thing I don't like about this example is all my categorical variables only have 2 levels. Okay? They're just, you know, smoker, non-smoker. So I can use a 0 or a 1, a single dummy variable. But remember, we talked about this last week, that the number of dummy variables I need is 1 less than the number of levels. So if I had non-smoker or lifetime non-smoker, someone who's not a non-smoker now but used to smoke, and then somebody who's a smoker, a current smoker, that would be 3 levels. I would need 2 dummy variables. Okay, so I would need 2 dummy variables. But here, I only need 1 because I only have 2 levels or 2 categories within a categorical variable. And so I just make them 0, 1. And the way I did that was I just sorted them by that particular thing. So for instance, I went here and highlighted this. And so like the sex of the baby or gender of the baby, I said data, sort. And I could do it by smoking. I did, at one point to work with that, but, sex of the baby, I say okay. And so now all these female, I just went in and changed them to zeros. Now, not on the original data, on a copy of the data, but I changed them all to zeros. That was the base case, and then changed the males to ones, did the same thing for smoking and premature and full term. Okay, so we had that. Now back to this cleaned up stuff. So now you see the zeros and well, you can't see the ones. They're down there somewhere. There are some ones. Okay, so those are the dummy variables going in. So I have all those. I just run the thing, and what I see here I've got my p-value of 0.08 for smoking. Not quite significant. Okay, not quite significant. And I've got my other p-values for the other variables. Now, so the idea is, well, should I have all these variables in there? I already got rid of one. I got rid of father's age. Okay, well, as we look at it, so I notice like there's weeks, right? Number of weeks of the pregnancy and whether the pregnancy was premature or not. Well, that should be very, very highly dependent, because premature or full term is defined by the number of weeks. So if you go 37 weeks or more, you're full term. If you go fewer than 37 weeks, you're premature. That's simple. So what you can do is we could do a plot like we did before, and let me try that. So weeks and premature, do I have that plot? Yes, I do. Okay. So I plotted it. Now, I like putting I put the weeks as the response and the premature as the explanatory variable. You could do it sideways, kind of turn that on its side, and that would be fine as well. But notice, it definitely looks like there's a negative slope there. I could put that into an analysis of variance as well. Now, what I did was I just put the two of those into a linear estimation thing. Oh, I didn't check the ratio here. Let me do that real quick. Equals absolute value of the slope divided by the standard error, and we're going to get a really big number here. I am darn sure that's going to be a very small p-value, right? Because that's our number of standard errors. We only need to be at like 2, well, with 147 data points, we only need to be at about a 2. And we're at 14.8. So we're down there probably 10 to the negative 20th or something like that. We can check it just to show that we can, and it doesn't take long. I need that value. I need the degrees of freedom, which I get right there, the 145, and then a 2 for a two-tailed test. Hit enter. Yeah, 10 to the negative 31st. Really small. Okay, so my p-value is very, very small. We should get rid of one of those two columns. Now, since premature has a lot less information attached to it than the number of weeks, I got rid of premature. Okay, now something else to look at though is here's the adjusted R-squared that we talked about last week, and it is 0.5. It says about 50% of the variance in Y is explained by our model. Now, if I go to no father's age, no preemie column, and I run this again, actually the adjusted R-squared goes down a little bit. Okay, does that mean I should put the preemies back? Well, probably not. Okay, so that's the thing, is adjusted R-squared is not everything, and it only went down from a 0.50 to a 0.49, not really much difference. But also notice what happened here. So before, if you look at the various p-values, so the premature, we got rid of that, but it was highly significant. 0.02, way under 0.05. Well, at least kind of far under 0.05, right? But notice weeks was 10 to the negative sixth. And they're really one and the same thing, right? Weeks are telling me the same information, actually more information than premature. So, that's where this is not an exact algorithmic thing. Oh, you look at the p-value is big, get rid of it. P-value is small, keep it. No, because there's also the covariance aspect. And, oh yeah, and I plotted that here. Now I have added a link to this site. Here's a nice site where you can put your data in and get a nice box plot that you could, take a screen capture of and plot in your stuff for like your final project. But there, so there's the same sort of stuff plotted, and on the plot with mine, because of the thickness of the squares when it plotted it and so forth, it actually looks like they overlap a little bit. But again, by definition, they shouldn't. And if we look at the box plots there, the box plots don't overlap at all. So again, that just seems like, oh, that is saying the two means are probably very different. And I could check that with, an analysis of variance, but I also did it with the linear regression. And with the linear regression, had a really tiny p-value, 10 to the negative 31st. So, and that's exactly what I would get with my analysis of variance, is that same p-value. Okay, so I get rid of that. So now I'm down 2 columns, father's age and the premature. And I run this again. And, well, the adjusted R-squared went down just a tiny bit. But notice here, the p-value for what I'm interested in actually also went down. Okay, I got rid of that redundancy of premature and number of weeks pregnant, and all of a sudden the smoking part is starting to look a little more significant. Not a lot, because before it was 0.08, so it didn't drop a lot, but it dropped a little bit, and we aren't quite to the 0.05 threshold. And again, and what we're going to see at the end of this is we get down to like 0.04. Well, so do you keep doing it till you get the answer you want? Well, no, not really. If this was my data, my stuff, and I finally, I whittled all this down, I got down to 0.04, probably I would say, I think I should go collect more data again and check this out more carefully. Because it is so close. But technically, if we get under 0.05, we get to say, oh yeah, it's significant and we think there's a dependency. Okay, so I get rid of those and I look at it again, and the adjusted R-squared, as we said, went down a little bit. But then I also look at things like p-values. And so the sex of the baby, that p-value is huge, 0.66. Number of visits, that p-value is pretty big. The weight gained, big p-value, right? All of those are candidates to get rid of them. Now, do I have? Yeah. Okay, so I started thinking about the same thing with premature and mature, or premature and full term. And I thought, well, you know, the number of visits you get in is going to have to do with how long you carried that baby. Right? If you go full term, you can have more prenatal visits. So maybe I should look at that. Now that is actually the smaller of those three p-values. I've got a 0.66, a 0.23, and a 0.11. So the 0.11 is the smaller one, more towards significant, but it seems like an obvious problem of dependency in the explanatory variables. Again, the longer you go in the pregnancy, well, the more visits you can have. I mean, sure, of course you can. And so I plotted that, and that doesn't look as strong, but notice again, so I went ahead and did a regression on that, and got something significant here. It says that there is a bit of dependency there. Now, the R squared, not very big, 0.09. It says 0.95. It says only about 10% of the variation is explained. So there's a lot of variation in prenatal visits. Maybe I should keep it in. I decided not to. Okay, was I right? Not if you disagree with me. In that sense, right? I made a choice of throwing that one out first. Somebody else may have made a choice of throwing out the, I don't remember which one it was, the sex of the baby, the gender, throwing that out first. Okay, but I decided to throw this one out first. Again, I see that ratio. If I check the t-distribution for the p-value, I have that. There's my degrees of freedom, two-sided test. And you see I'm down a p-value of 1/10,000th, or 14 100,000ths. So that's really small. Okay, so sure, I'm going to throw that one out. Somebody else may say, nah, I don't want to throw that one out. Okay, but yeah, I threw it out. And so then I got to just these columns. So weeks, the weight gained, the sex of the baby, smoking, and then the weight of the baby is the response variable. Now all of a sudden, I'm down in the significant area for the smoking. And what I'm seeing is the slope says negative 0.388, so about negative 0.4. And the way I interpret that is if the mother doesn't smoke, then the baby has a certain average weight. If the mother does smoke, subtract 0.4 pounds. Okay, nearly half a pound is what that's saying. And, it's not extremely probabilistically or statistically significant, right? It's at the 0.04, so not a lot under the 0.05. But in a practical sense, if that is the slope, nearly half a pound, 0.4 pounds, that's a big deal to a newborn. And so this would be information a person would really want. So very, very applicable answer in all of this. Okay? And so that's what we found so far, but notice we still have, under the sex of the baby, the gender, that p-value is still up there around 0.6. We probably shouldn't bother putting that variable in there. And, and I'm not comparing it to any other variables at this point. In this case, I'm not worrying about that whole covariance idea and dependency among the explanatory variables and the confounders and so forth. I'm just looking at it as it doesn't seem to matter. Okay, now that's contrary to what I understand being true, but at least in this data set, it doesn't seem to matter. Because again, now I could be wrong, but I believe it's pretty well established that females tend to have a higher birth weight than males. And that is also why, or well, not the reason why, but that is part of the reason why their males are actually more likely to succumb to various problems when they're first born. And so, I'm kind of surprised that at least in this data set, it didn't seem to matter at all. And so the next thing I did was I went ahead and I took it out. And when I took it out, now notice, we should also look at the adjusted R squared. So back here, the adjusted R squared went down a little bit right at first. But now, as I'm taking things out, it's, did it go down a little bit again? Okay, so it went down a little bit yet again, but not a lot. And now when I take out the visits, it actually went back up just a tiny bit. So it's all been around 0.5. Nothing's really dropped, nothing's really gone up. So the adjusted R squared really hasn't been a factor in all this. And again, as I look at the significance level, now here's something again interesting. P-value here was 0.043. When I took out the gender of the baby, it jumped up just a little bit. So does that mean, I should put it back in because what I'm after is a significant result for my, whether smoking matters? No, right? I had good reason to take it out. And then I see that the model's now saying, smoking's still significant, not real significant, but actually just a tiny bit less significant than it had been under the other model. Oh, bummer. Okay, I would hope it'd keep going down. But that's the thing. You really have to follow what you're working with. As I looked at it, that p-value was so big, it just didn't seem right to keep that data column in. And now finally, I see that the weight gained by the mother, that's still not significant. Other things are at least somewhat significant. Now the age of the mother, not very, it's a little above the 0.05, but I might keep that in just because it is down there. And so I take that out and I'm down to just 3 explanatory variables. Smoking, the length of the pregnancy, which, by far is the most significant thing. Absolutely by far, right? Because it's 10 to the negative 22nd. And then the mother's age, that is still up there a little bit. The adjusted R squared, what happened to that? It's 0.486, it was 0.489. So again, the adjusted R squared, it's kind of holding about steady. It dropped just that tiny, tiny bit. And so the question is, do I do it one more time and get rid of the mother's age? You know, so maybe I didn't need the mother's age nor the father's age. And I can. And I'll show you, here's how I do this so it's not lots and lots of work to do this. Okay? I just go down here and right-click on the current page, the current sheet I'm on, and I say, okay, I want to copy or move the sheet. I'm going to choose copy. I am going to put it down here after all my other stuff. Now I've got a couple other things in here that they were from Tuesday and didn't matter. So I'm making a copy. Right now it's got this name. It puts a 2 on it because I'm making a copy of it. Now I've said no and gotten rid of all these things. And the last thing I'm getting rid of, what the heck was I getting rid of? Age. Yeah, mother's age. So mother's age, and so I say okay, and it makes that copy. And now what I do, and I think almost any spreadsheet's going to let you do this, I just come over here and I right-click on that and I say delete that column I don't want. Now notice this all still works. It's got a bunch of NAs over here. And so just to pretty it up, what I can do is I can highlight all of it at first, and then I just clicked up in the top line and I copied everything except the equal sign. So just a Control-C to copy it. The reason I didn't do the equal sign is if you try to paste everything in when you do this, it doesn't work. You have to type the equal sign first to get it to do it. But so I just copied that command because it's the right command. Okay? Because I deleted that column, it adjusted everything correctly. And because see, it only, if you look at it closely, the explanatory only does columns A and B. That's correct. And so that's the right thing. Well, I don't want to type it all over again and so forth. So I copied it. Now I do a Control-Shift-Enter just to put it back the way it was. And then I didn't need to click that. So I highlight everything, get rid of it. And now I just highlight the part I need, those 3 columns now, and I type equals, and then I paste and do my Control-Shift-Enter, and it's all there. And then I just need to move my intercept over. So that's kind of what I did with all of them. And that's the new regression. And notice, oh, that's great. The p-value is now down to 0.03 once I get rid of that. But everything I just am using 2 columns now, but they're both very significant. And so what I could say at this point is, because I started with all those other variables, I can say we find a significant, well, you got to be careful about the word significant. Yeah, so here we could say we find a significant difference between, in the baby weight, so mention the response, in the baby weight between mothers who smoke and mothers who don't smoke. With mothers who smoke having babies at about 0.4 pounds less than mothers who don't smoke. And then here's the important part with the confounding variables. That's even accounting for father's age, mother's age, whatever else we had in there. well, weeks, length of pregnancy. I mean, that's definitely still in there. And whatever else gender of the baby, and all this. We put all those confounding variables in, we checked it, and we still end up getting this significance, and this is what we would probably report, saying, oh, the very significant thing is just the length of the term. Now, but see, here's the question, right? Here's a new research question out of this, is I found a dependency. But the question is, does smoking cause the lower birth weight? I have no idea. One answer could actually be what smoking could cause is an early birth. Right? And how would you check those things? Well, you'd start looking at things like ultrasounds and estimating weights and doing that along the way, right? If everybody at 20 weeks, whether they're a smoker or a not smoker or non-smoker, the babies weigh about the same, right? You then start thinking, oh, well, maybe the smoking actually causes the mother to go into labor sooner. Oh, new answer, right? It's not actually reducing the baby's weight, it's reducing the length of the pregnancy. Oh, could be. So you could start looking at that, right? So usually anything like this, it's an observational study. It leads you to some ideas to explore more things, but I don't know a cause. Okay, no cause here. And I can picture that, well, there could be a cause that smoking is doing, right? Smoking is a cause of something, but it's not the low birth weight. It could be the cause of premature labor. But who knows, right? So this is the idea. This is why your final project should take you a while, right? Because this is how you want to approach talking about your study. You don't want to just say, oh, yeah, I'm interested in smoking and birth weight, and so I look at those two variables, and there you go. No, that is not complete. That will not score well, because that is a crap study. Okay? And we are trying to show that we've learned something about what it takes to make a reasonable, robust statistical analysis. And there, we do need to worry about confounding variables. Now, depending on what you're looking at, you might have to attack those confounding variables differently. But one way is definitely multiple regression. You can just kind of throw everything into a multiple regression, but it still then takes some work after that. And again, you may, your data, you may have to create your own data. We'll talk about that next week. Just because you don't have data, you may go get some data off the internet that you can use. Again, you don't have to come up with a real answer. This to me is not a real answer. I don't know where these data came from. But I can still talk about, if I were to do a study like this and these were the type of variables I got, this is how I would approach it. Okay, and I would finally get some sort of answer. My answer was not far off from being a big bust, right? I mean, I'm down to 0.03, but that's not far from 0.05. So, and that's okay. Again, the project, your final project, is about the process, not about the answer you get with some particular set of data. Okay? All right, so I will see you next Thursday. Have a lovely week.